Okay, good afternoon, everyone. My name is John McCorry, and on behalf of IGEM and the Pipeline Industries Guild, I'd like to welcome you all to this afternoon's webinar, Safety of Hydrogen Blends in the Northern Irish Gas Network. Just some webinar etiquette before we pass you on to the guest speakers today. Your microphone has been muted and camera switched off automatically. This is to help maximize the call quality and for the speakers to give the best presentation possible. We will be taking questions after the presenters have spoken. So the best way to submit your question is via the chat facility, and hopefully we'll try and answer as many questions as we can, depending on time after the presentation. The presentation is being recorded, and the webinar is available for you afterwards once it's downloaded via IGEM TV. So I'd like to welcome our speakers today. They are Owen Wilson, who's Network Safety Manager in Gas Networks Ireland, and Dr. Sheila Brennan of University of Ulster. This webinar is introducing an 18-month project focused on the safety of hydrogen blends, specifically on the topics of buried leaks and flame stability. So without further ado, I'll pass you over to Owen Wilson, who'll give you a bit more of an in-depth of himself and Dr. Sheila, and a bit more scope on the actual presentation itself. So thank you.
Thank you, John, for that introduction, and good afternoon, everyone. And thank you to IGEM for hosting this event, and to IGEM and the Pipeline Industries Guild for promoting it. As John said, I am Owen Wilson. I'm a Network Safety Manager of Gas Networks Ireland, and we are, through our subsidiary GNI UK, one of the industrial partners on this project. The other industrial partners are Phoenix Energy, who are represented on the project by Brian Dawson, and Mutual Energy, who are represented by Emmett McFadden and Niamh Kyle, and they've joined us on the webinar today. The project itself is a joint project between Ulster University, led by Dr. Sheila Brennan, and a group of industrial partners. And the correct full title of the project is Safety of Hydrogen Blends in the Northern Ireland Gas Network. And the project studies a number of aspects of hydrogen and methane safety, which will ultimately help inform the safety case demonstrations that we, and I imagine most of you on the call, as gas network operators are required to make to our relevant regulators. The work brings Ulster University's academic and research expertise in hydrogen safety together with the gas industry to help understand some real-world practical industrial needs. I must give full credit to the sponsors of the work, funding of the work, and forgive me if I read this, but it's funded by the Centre for Advanced Sustainable Energy, which we all know as CASE, and CASE themselves are funded through the Department for the Economy, Northern Ireland's Green Innovation Challenge Fund, and aims to transform the sustainable energy sector through business research. It's a little bit of a mouthful, but we have to give them full credit for the funding of this project. Before I hand over to Dr. Brennan to take you through the project and some of the work that's been done to date, I'll just remind you there is an opportunity at the end for questions. So if you have anything to ask, please put it in the chat function, and we'll do our level best to get to it at the end. Now, if I can hand over to Sheila, and she will take you through the project in detail.
Thank you, Owen, for the introduction, and thank you to both IGEM and the Pipeline Industry Guild for facilitating today as well. I'm just going to share my screen, which hopefully you can see okay. So what I'd like to do today is talk you through, as you've heard, an ongoing project. It's an 18-month project on the safety of hydrogen blends in the Northern Ireland Gas Network. And I'd like to really tell you about what our plans are, what we've done so far, and maybe invite your questions and your input to this. We believe safety is key to underpin the safe introduction. So for us, it's very important to disseminate the activities we're doing, to share the information and to get feedback as we go. But I'd like to give a bit of context before I begin in terms of the team that I'm speaking on behalf of, the High Safer Centre at Ulster University, and then where this project came about, an introduction to it, what's the rationale for it, how it is structured and what the timeline is around that. And there are a number of research strands within the project, but the two primary ones are flame stability and buried leaks. So I'm going to talk through what I mean by those, the type of work we're doing on them, and how far we've come and what our next steps are. And hopefully there'll be plenty of time at the end for both discussion and questions. And if there are things that we don't touch upon through this project or through this presentation, or if you've questions at the end, my email will be on the last slide and I'm very happy to share it. So I would welcome questions following this also. So I'm speaking on behalf of the HiSafer team at Ulster. We're a 4-campus university, and I'm based within the Belfast campus from the Faculty of Computing Engineering and the Built Environment, and specifically within the Hydrogen Safety Engineering and Research Centre. I'm a mechanical engineer by background, but I teach across a number of the engineering courses, and my main research area is in hydrogen leaks and fires. So HiSafer at Ulster. So I'm speaking on behalf of the team and the hydrogen safety team at Ulster. And the work that I'm going to present while I'm leading the project has been performed by a number of colleagues. So I think it's important to note that. So what do we do at HiSafer? We're very much focused on hydrogen safety, as in the name. And the type of work that we're doing is fundamental and applied research on hydrogen safety, specifically or generally consequences following the loss of containment. So that might mean leaks, fires, explosions. And we are a simulation team. We undertake analytical and computational modelling. We don't undertake experiments in hydrogen safety at Ulster, but rather we partner with teams elsewhere. A lot of our funding comes from Europe, but we've 12 ongoing projects and they're all focused on hydrogen safety. They're collaborative projects, both with industry, with other academic partners, and with experimental partners globally. Our funding is predominantly European, but we also have UK funded projects and those from Northern Ireland, which this is an example of today. And where we use this work is our focus is on understanding how hydrogen behaves. If you can understand it from a fundamental perspective, you can use that information to inform engineering design. And then in turn, we use that information to further inform codes, standards, guidance documents, as this project will feed into, and also innovative engineering design. So I'm going to talk through just one aspect of the activities that we're involved in today, but we do undertake more wider research as well. So as I mentioned, our key really is the type of work we're undertaking at Ulster is closing knowledge gaps, addressing technological bottlenecks in hydrogen safety and using that information. So we do work closely with industrial partners, and this project is one example of that, to ensure that any research we're undertaking has real impact and can be used in a real life setting. We're represented on a number of standards bodies and use the outputs of the research to inform those documents. We have experience in the development of simple tools. So while we're undertaking our 3D simulations, we use that to build simpler models that can be used by anybody. So what I have as an example on this slide is a screenshot from our e-laboratory, and I'm happy to share details on that. It's a free online tool where you can, for example, if you want to know the extent of a hydrogen leak, you can put in your pressure, your leak diameter, and it will calculate the distance to the point at which you have a leak that is no longer flammable. And we also deliver education and training in hydrogen safety across all levels. We have postgraduate studies, but I've recently led a project on delivering training to firefighters in hydrogen safety. So that brings me to this particular project, which is focused on hydrogen blends. And we all know that there's plans to decarbonise the Northern Ireland gas network, and hydrogen is just one route to do this. But our existing infrastructure and the guidance, both on leak management and the safety plans, are all for natural gas. But natural gas and hydrogen are different, And if we need to understand what implications that has. So do those differences, do they have a bearing upon our existing guidance documents? Do the different hydrogen and methane properties mean that we need to make amendments? Is the existing guidance fit for purpose, or does hydrogen behave differently? So that's really where this project fits in. There's many research gaps. We've had a workshop and ongoing activities looking at what those might be. And this project is just picking up on a few of those. But just to come back to, I mentioned that hydrogen and methane are different. And this may be, and I'm referring to natural gas as predominantly methane, and will do throughout this presentation. So my stance on this is hydrogen is no more or less dangerous, it's just different. But if we can understand those differences, then we can use that to benefit. So if we consider the flammable range in air, so in the case of natural gas, that's relatively narrow. It's between the region of 5 and 15%. Hydrogen is much wider. So from a percentage by volume in air of 4% up to 75% hydrogen in air, there is potential for ignition to occur. And ignition, you need a lot less energy in the case of hydrogen in order to ignite it. So really what we can take from those two first rows is that in the event of a hydrogen leak, there is a much greater chance of an ignition event occurring. There's a wider range of concentrations over which it's flammable, and you need a lot less energy in order to cause that ignition to arise. It's a lot lighter though, and that's one of its greatest safety assets. You know, the example I always use is if you're holding a helium balloon and you let go of it, it's going to shoot up, and hydrogen is lighter again. So its buoyancy relative to air is a great asset. But all of these differences have an impact. So in the event of a leak, it's important for us to understand, if we move from natural gas to hydrogen, how will it spread? Will it spread differently? Will your flammable cloud be larger? Will it be smaller? And all of those areas are things that we're interested in looking at, because they will ultimately impact upon the operational activities, maintenance, and specifically the emergency response procedures of the gas operators. So that brings me to our project, which is the safety of hydrogen blends in the Northern Ireland Gas Network. And there are many, many issues that we could be looking at from a research perspective, but we are picking up on just 3 of them within this project. So it's an 18-month project. We're at the halfway point. We started in October. And as you've heard, it's together with 3 of the gas operators here in Northern Ireland. And our real goal is to undertake pre-normative research, so that fundamental research with the goal of informing safety guidance. And we're undertaking this research in 3 specific technical directions. And I'll explain more shortly what I mean about each of those. So we flame stability of hydrogen methane blends. So that's really down to, for a given leak, will you have a flame? Will it be sustained or will it blow out? And I'll explain what I mean by that, and what is different as we move from methane to hydrogen. Buried leaks, so leaks from pipelines that are underground, where you have a leak that may permeate through the surroundings. Where does it go and how does it spread? And we are also interested in injection and mixing. So what I mean by that is where you are injecting hydrogen into a methane pipeline, how, after what distance from that injection point will you have perfect mixing? Does the means by which you inject it, so the orientation of the injection, the pressure ratio and so on, what bearing does that have upon the mixing process? And I always say that this project represents phase 1, because we do hope to build upon it and to continue activities in this direction. And there's a lot of research gaps, and we're keen to move forward with this activity. So in terms of the actual project and how it's structured, we have 4 work packages, and all partners are actively involved in each work package. And for us as academics, this has been incredibly useful to have such close interaction with the gas operators and feedback in terms of focusing the direction or our matrix of simulations. But we do welcome wider stakeholder input, which I guess is where this webinar fits in as well. We're very interested in feedback. We believe safety is key. So it's important for us to share the knowledge, share the findings going forward. So we started with scoping out what the state of the art was in work package 1, and we completed that just before Christmas. So what's existing safety guidance in place? What are the safety cases like for the operators in Northern Ireland? Where might the work that we're doing feed into those? What might they potentially impact? What elements? What are the potential hazards and associated risks? And within the scope of those, what are we looking at and how does it fit in? And we also analysed by RCS there, I mean regulations, codes and standards. So what is governing operation in Northern Ireland, and PNR, so pre-normative research. Who has done what elsewhere? This is a very topical area beyond Northern Ireland. There's research ongoing on the safety of blends globally. So we undertook an extensive literature review around the topics that we are investigating to make sure that we are accounting for work that has already been undertaken. So that work package completed before Christmas and set the scene for the core research. And we're undertaking that in 2 main directions. So leaks and dispersion behaviour of blends in pipelines. So that covers releases from pipelines, injection into pipelines, and the end goal is safety recommendations. So what we're doing this, we're undertaking this research with an end goal in mind, and that's to inform guidance and make recommendations. In parallel to that, we're looking at flame stability. And there's some terms there that I'm going to explain in a minute, from critical diameter through to flame stability curves. And again, with that action, it's what are we going to use with that fundamental research? What's the output? And our goal is to use it to inform guidance documents. And around all of this, there is, of course, administration and management of the project and reporting upon it. But outreach and dissemination is a really important part of that. So as academics, we're publishing the research in academic journals, but our wider stakeholders are very important to us. And this webinar forms part of that outreach activity. So I'm going to talk through flame stability as the first element. And what do I mean when I talk about this? So a flame arises when you have a leak, which is then ignited. But a flame isn't necessarily sustained. So what I mean by that is if you have a leak of gas and that gas is flammable, even if that gas continues to leak following ignition, you may not always have a flame. You can have a scenario where that flame blows out. And that will arise if your leak diameter is small for a particular driving pressure. And why that might be important is if that leak arises in a scenario where then you've got accumulation of a flammable gas and you no longer have a flame. So understanding this relationship between leak diameter, flame behaviour, and what you're most likely to have is important from a safety perspective, so you know what you're dealing with. And different fuels behave in different ways. There's quite a difference between the situations where you would have a flame for methane versus a flame for hydrogen. And that's what we're looking at. And there's no or very little information out there on what arises when you have a blend. And why this is important is from a safety perspective, knowing if you're likely to have a flame sustained when you have an ignition source or you're not. It has implications for equipment, guidance, safety cases. And as I said, hydrogen and methane are different. So I'm going to talk through where we started with this. So before I do that, some basic concepts around it and what do I mean? So what I have shown on the left hand here is we use simulation. We use software at Ulster, three-dimensional fluid dynamics software, CFD, in order to simulate leaks and fires. And what you can see on the left-hand side of this is a temperature profile, and it's a slice through a jet. So over on the furthest left point of that image is where your jet is leaking from. And what is shown is the temperature profile. And how we know it's ignited is because you've got a temperature there of 2,400 Kelvin at the center. So what we have here is a flame, and it can be attached. It might be lifted. So what that means is where you have a flame emitting from a leak, the base of that flame may be a little bit above it, or it could be attached to the release point. But we don't always, if you have a leaking gas and it's flammable and you have an ignition source, we don't always have a flame that is present. It depends on both the pressure that is driving it and the leak diameter. But that image is really to show you what a sustained flame looks like with our software. Because in reality, a hydrogen flame burns with a pale blue flame. We often say that it's invisible. And this image is showing a comparison of a hydrogen and propane flame. In reality, what we see through experimentalists is for larger scale flames in particular, you can have entrainment of particles or dust particles, which can help visualize them. But generally, a hydrogen burns with an invisible flame. So we have this sustained flame concept. We also have something called blowout. Okay, so this is where, for the right combination, or wrong, depending on what you want, of pressure and leak diameter, you can have a flame that, when you remove your ignition source, it's not sustained. Instead, your hot products move downstream, and that can leave an unignited leak. And maybe that's okay. Maybe it's in an outdoor environment and you're not concerned about how and where your hydrogen or methane disperses to, but in a confined space, that can be problematic. And what can drive this is something called your critical diameter. And what a critical diameter is it's the minimum diameter above which a flame will be sustained at any driving pressure. And in the case of hydrogen, that's 1 millimeter. So what that means in practice is if you have a diameter leak, or a leak diameter that is 1 millimeter or above, so that's quite small, and you have a hydrogen leak from it, and its concentration is in the flammable range, when you ignite it, provided you keep the fuel source there, it will continue to burn. However, if your leak diameter is below that, so a very small leak diameter, you can have a situation for a given pressure, your flame isn't sustained. Instead, it blows out, and it is, and again, this can lead to this accumulation of a flammable gas. So we wanted to model that, and at Ulster, we can predict different behaviour, but generally, before we model something, we start with some experimental reference, so data that somebody has actually measured of the phenomena. And we use that to validate or check our models so we have confidence in how they behave before we use them to predict other scenarios. So what this image is showing is experiments that were a summary of experiments that were taken by a Japanese group undertaken back in 2009. And what this is it's a flame stability curve. So along the x-axis, we have the diameter of a nozzle. So that means your leak diameter. So if we assume, for example, a perfect hole, and I know you can have cracks and fixtures and fittings, but for the sake of this, we're looking at a simplified case, a perfect hole or nozzle. So along the x-axis, we have the diameter of your leak. And along the y-axis, we have the driving pressure. So that might be tank pressure, pipeline pressure, and so on. And the measurements on the graph are in megapascal, but I've put bar on the to the side of them there for reference as well. And what this diagram shows us is for different combinations of pressure and diameter, the type of behavior that you're likely to have. So on the lower end of this graph, we have a solid line, and anywhere below that lower curve, for any combination of pressure and diameter, you will have a flame. We also have an upper solid line there. Anywhere above it, any combination of pressure and diameter, you will have a flame. We say it's a lifted flame there. But in that middle region, inside that peninsula shape or that curve, we have a blow-off region. So for combinations of pressure and diameter that fall within that region, your flame will not be sustained. and you can have a leak where it leads to an accumulation of a flammable atmosphere. So if I was to take the example there of 10 bar or 1 megapascal and 0.5 mil, you would not be able to sustain a flame. Anywhere to the right, if I go again along the x-axis here to 1 millimeter, and I go up anywhere to the right of that point, you will always have a flame. So this was experimental data, and we wanted to show that we could reproduce this. And we wanted to check our modeling capability and see what it would look like if we simulated flames in this region. So before we could reproduce a curve, we wanted to check we could reproduce the basic flame behaviour. So we have 2 columns here, column A and column B. And column A shows a leak from 2 bar through a 0.9 millimeter diameter, so it's pretty small. And column B shows a leak from the same pressure, but this time through a 1 millimeter diameter hole. And as you move down through the rows, it is an increase in time. And what you're looking at is temperature contours here. So at the very top row at 4 milliseconds, we have a leak and we ignite it. As we increase with time, what you see in the left column is that flame is not sustained. Instead, your hot cloud starts to move away from the leak and moves downstream. Whereas on the right-hand side, it is sustained. And what that really demonstrated, or why we simulated this, was to check that we could accurately capture this behavior of either a sustained flame or blowout with computational fluid dynamics. So this was our starting point. Then when we knew we could do that, we undertook some simulations around this 1 mil region to check that we could accurately simulate this critical diameter. So for example, for the same pressure of 2 bar, if we had a leak from 0.8 mil, 0.9 mil, 0.95 mil, we showed it blew off or blew out. And as we went from 1 mil and above, the flame was sustained. So once we had confidence in that, we then predicted this overall curve. And this gave us confidence that we could predict for any combination of leak diameter and driving pressure, we could predict flame stability. So this was our starting point. As I said, I'm representing the Hydrogen Safety Centre. So we started with hydrogen rather than methane, but the natural next step was then, rather than go to a blend, go to methane. So in this case, you can see the flame is, rather than horizontal, it's vertical. And the reason for that is, again, we checked against experimental data. So there is data available for pure methane. There was data available for pure hydrogen. There's nothing for blends. But if we have confidence that we can predict how hydrogen behaves, and we have confidence we can predict how methane behaves, then we know that we can, with relative confidence, predict the behavior of blends. And in this case, what you have on the top row is, again, from 2 bar pressure, we have a leak through a 43 mil orifice. And on the bottom row, we have a leak through a 41 mil orifice. And in the top row, as you move from left to right, it's with increasing time, and you can see that the flame is sustained. On the bottom row, as we move from left to right, the flame blows out. And what's interesting about this is, in this case, the critical diameter for methane is just over 41 mil. It's around 42 millimeters. So why does that matter? It means that in the case of hydrogen, if you have a leak at an ignition source and your leak diameter is above 1 mil, you will always have a flame. However, if you move towards methane, it's different. You need a leak diameter, which is quite a bit bigger than that. You need a leak diameter of 42 mil before you will always have a flame. Okay, so what this gave us was confidence in predicting that behavior and the difference between both methane and hydrogen. So to summarize on this activity, hydrogen has a critical diameter of 1 mil. And methane is much bigger, or relatively bigger. It has a critical diameter of 41 mil. So that means that in scenarios where you had a leak of natural gas, where you couldn't sustain a flame, if we now substitute that with hydrogen, it will be possible to sustain a flame. So this needs considered by designers or when considering incident scenarios. So we're not proposing whether this is a good or bad thing, but more analysing the differences and then looking at how we can use that to feed into guidance. So where we're going from this now is we have confidence, we can predict for given pressures, given diameters, if you'll have a flame of hydrogen, and we can do the same for methane. Now we're looking at different blend ratios. So what is the critical diameter for example, 20% hydrogen, 80% methane? And we're looking at that for a range of different ratios and predicting the associated stability curves. So that's one of the research directions. There are findings to date and where we're going with it next. The other main research area is we're looking at releases from buried pipelines. I'm not talking about pipelines in potentially the transmission network. We're not talking about where you may have cratering of the ground. So a combination of pressure and leak diameter that is sufficiently large that your ground is pushed up. But rather we're looking at cases where the gas disperses through the ground instead. And we particularly are interested in understanding the flow behaviour. So where does it go? How does it spread? Where does it track? With the idea that we want to understand and avoid the potential that that gas tracks into an enclosure, into a house, and so on. We want to understand what parameters influence the extent of that flammable cloud, what is driving it, with the end goal that we will inform safety cases. Because we want to understand where has the data, where have the values at the moment for methane come from? Can we understand those? Can we predict that accurately? And then what is different about hydrogen? And in this case, there's minimum quantifiable published data. So there's very little out there to date that has been undertaken. There has been some work done within High Deploy, which has been more qualitative in nature, where they have given an indication that hydrogen tracks further. But actually, in terms of concentration measurements from a leak within soil, there's almost there's little to nothing out there, apart from one study that we have found, and we are using, my colleague Shivam is using as a validation study. I'll come to that in a minute. And what we're interested in with this leak below ground is we want to understand the distance to the lower flammability limit. So if you have a leak, you'll have 100% either hydrogen or methane or blend at your leak point. And obviously, as that spreads out, it's going to entrain air and that concentration drops. And what we're trying to analyze for buried leaks is not the consequences of ignition, but rather the distance through the ground and above the ground for different scenarios, that the hazard distance to a given percentage of either hydrogen, methane, or a blend, because we want to understand the hazard distance or the furthest point from the leak at which it is not possible to ignite that cloud. So we have undertaken a validation study. There is a published paper by a Chinese group that have looked at dispersion through sand. So I appreciate there are not many pipelines in Northern Ireland that are buried under sand, but we need to have confidence in our modelling approach before we start to step away from it and look at different materials and so on. So what you can see on this slide is we have a leak from a 4 mil diameter from a 3-bar pipeline, and it's leaking through 10 centimeters of sand. It's kind of hard to see on that diagram, but you might see a thin blue line that's running horizontally across all of these contour plots. That represents the sand. So we have a buried pipeline, we have a leak, and that leak is spreading up from the sand. It's dispersing radially and and also vertically. And what these contour plots represent is the extent of the flammable atmosphere. So the scale that you can see in the legend on the left-hand side is the mole fraction of methane. So this is a pure methane leak. So you've got 100% hydrogen or methane right at the leak point, and then it spreads out. And we've capped it when it reaches 5% to demonstrate that the extent of the flammable cloud. We have looked at the distance of spread to lower concentrations as well, because obviously that will be important for sensors and so on. But this image is purely to show the evolution of that cloud. And what we have done is there is experimental data available for the first 60 seconds of this leak. That's why we chose this particular pressure, diameter, and depth of sand as a starting point. So we've compared our data to this. We've had a very good match, so we're confident in our modelling approach. But the published data only looked at that initial stage of the leak, the first 60 seconds, but not how it continues to develop. So you can see there, if we move 2 plots in on the left-hand side, what has been published and what experiments to date have covered has just been that initial stage. But we've used our simulations to show that that cloud continues to grow, and it grows for almost another 8 or 9 minutes before it reaches a steady state, as long as your leak continues and so on. And the type of measurements we're taking or output from our simulations are what is shown in the diagram on the right-hand side. What we have here is the time along the x-axis, and along the y-axis, the methane concentration. So you can see how it's growing both radially or horizontally and also vertically. And what we have been doing since this is not necessarily looking at that evolution of the flammable cloud, but rather looking at the end point. So what is the maximum extent of the hazard distances, both through the ground and above? And what we're trying to understand at the moment for methane is what influences that. So as I mentioned, we've compared against sand. Not all of our pipelines are buried in sand. So for different materials, how are the properties important? How does the porosity of the material, the density, or really the distribution of those pores, so the size of the granules, how does that impact the dispersion and spread? How does the depth of the pipeline, how is that important? What's the relationship between the pressure of the pipe, the leak diameter, and indeed the leak orientation? So we're currently undertaking a parametric study, and we're just closing off on the material properties and depth at the moment, and we'll be extending that to look at pressure, leak diameter, and orientation. When we've done that, we believe we'll have full understanding of what parameters influence leaks from buried pipelines, what their relative importance is, and how to quantify this. Our next step will be then to look at hydrogen for a number of these cases, and if we see a pronounced difference, then we will look at a blend for the different areas. So I hope that's given an idea around what we're considering in that direction. The third strand, so the primary research directions within this project are flame stability, so understanding when you will have a flame, what the combination of diameter and pressure is that is needed for that, and also these buried pipelines. But we are also interested in more fundamental mixing behaviour. So that's where you have a injection of hydrogen into a methane stream. And so the point of blending, and specifically starting with quite a simple geometry, so a T-junction, so you have a hydrogen pipe, potentially perpendicular to a methane pipe. What we're interested in is for different pressure ratios, for different diameter ratios, at what point you have a uniform mixture formed. You know, some of there's nothing in the literature published to date around methane or hydrogen injection into methane, but there is data out there for other gas mixtures, so methane into air and so on, and it shows that at the initial injection point, depending on the velocity ratios or pressure ratios. You may have a jet that shoots up and moves along the edge of the top of the pipe, or doesn't hit the center line, and it can take a distance downstream for a perfect blend to be formed. So that's what we're looking at the moment, and we're undertaking initial steps in this direction, but there's very little out there on it at the moment in terms of published information. So we're at the stage of validating our models so that we can predict some simple or fundamental pipeline behaviour. So where do we intend to go from here? So as I mentioned, the next steps are around flame stability. So that's stability curves for different blends. We're relatively confident at this stage that we can predict the critical diameter for 10%, 20%, 50%, 80% hydrogen and methane, but we haven't presented it here. And now we will be using that information to develop flame stability curves as well. In terms of buried leaks, we're undertaking a parametric study. And the key parameters we're looking at within that are the material properties, so specifically the porosity, the pressure, the density, the diameter and depth. Well, actually, density, what we're seeing is it's not the density of the material is as important as really how your the size of your granules or how they're distributed. Your particle size, that's pretty key in terms of killing the momentum, for want of a better way of describing it, of your jet. The depth of pipeline burial, how that impacts the relationship between your radial and your vertical spread. And then using this information, once we have a full understanding of it, to compare what makes it different for hydrogen. And as I said, where we see a pronounced difference, we will then look at blends. So with flame stability, there's a clear difference. You're talking about 1 millimeter diameter, critical diameter for hydrogen versus 41 for methane. So we wanted to understand better what happens in between. For buried leaks, we don't know yet if there's going to be a significant difference between hydrogen and methane. That will be our first step. And when we know if there is, then we will look at blends. If there isn't a significant difference, we'll be able to give that margin of worst case hydrogen versus worst case methane. And where we're at in terms of pipeline mixing is we're looking at validating our models for injection into a T junction. And our next steps for that would be understanding if you inject horizontally, if you inject vertically, if you, so the angle of injection, the relationship between the pressure in your main pipeline, your injection pipeline, and respective diameters, what influence all of that has. So I'd like to finish up there, and hopefully that should leave about 10 minutes if you have any questions or feedback, and I'd like to open the floor for further discussion. My email address is there, and I believe that the recording will be available after this as well. So if you leave today's webinar and a question occurs to you in a week's time, please do not hesitate to get back in contact with myself or with the wider consortium in the project.
Thank you, Sheila, for that. Fascinating stuff, and I'm involved in the project, and I still find it fascinating, all the work that's going on. There's one question in the chat from Jason McCammon. I hope I pronounced that correctly. The increased stability of the hydrogen diffusion flame with regards to blow-off risk, is this due to the higher burning velocity of hydrogen?
Potentially. We're trying to understand at the moment what governs that, what governs that flame stability. So I think the burning velocity is important. This position of there's a concept called your waistline as well, which is to do with the point your concentration distribution if it's an unignited jet. So yeah, there's a few mechanisms. My colleague Minna Kazemi has been undertaking this work and has been looking through the literature at the reported mechanisms that govern that flame stability. And there is still a few different theories presented in the literature, I guess. So I can certainly share that information as well.
If anybody else has any questions, please put them into the chat now. Let's give people a minute just in case anyone wants to ask anything. Okay, so a couple popping into the question now. Gerald Fitzgerald. In relation to flame colour, what percentage of hydrogen blends does it start to become visible? Low carbon hydrogen is 98% pure. Is this a visible range?
That's a great question, and I don't have the answer to it, but it is something that now I'm interested in investigating as well. It's what I was cautious of stating with, you often do see and hear that hydrogen burns with an invisible flame, but what we see, we tend to, certainly in High Safer, is our focus to date has been on high pressure leaks and large diameter. We look at, from a hydrogen perspective, we're often interested in those that would be typical of onboard storage on vehicle tanks. And in those cases where you've such a high momentum leak, there generally is something entrained within it, particles in the surrounding ground and so on. And it tends to not be completely invisible. But I would be interested I don't have an answer to that. And I would be interested to follow up.
Okay. Again, here's one from Benjamin McAllister. To what levels can the impurities present in natural gas affect the results of the study?
So we are making the assumption of pure methane in the case of, so there's a few different elements to this. If I take the flame stability as a starting point, we have only predicted the critical diameter and flame stability for 100% methane. We could potentially look at if there's data out there around critical diameters for slightly for different constituents as well, or mixtures. I wouldn't expect it to have a huge bearing on it, but it is something we can take into account. We're now looking at it more for pure hydrogen and pure methane, and then we can take it from there. But that is something that we haven't factored into. I don't believe that it would have a significant impact on it. It's the hydrogen element that is having the bigger impact on it, but we can certainly look at that. In terms of spread or dispersion, I would imagine those small percentages of impurities, if we consider from buried leaks, would have a negligible effect on the hazard distances. And we're also approximating this within a couple of percent. So I don't think those small impurities would have a big bearing on it, but it is it's something that we should note in our assumptions, I think.
Thank you. From Mark Kelly, very informative, thank you. Was the 1 millimeter versus 42 millimeter hole size at 2 bar?
Yes, so that is all at so those flame stability curves, how they're described in some of the literature is almost like a peninsula or like a reversed C shape. And the critical diameter represents the apex or the furthest most point. So that occurs at 2 bar. So anything above that diameter, you will always have a flame. For pressures that are either above or below 2 bar, then you start to move left on this curve, and you won't. We picked basically the furthest most point on that curve for that scenario.
Okay. I've a question here from Peter Hart. Would you agree that it looks as if the safe setback from pipelines will need to increase for hydrogen blends? Since we can't easily move either houses or pipelines, can the setback be mitigated with lower pressure or other means? So I think what he's asking is, do we think that hydrogen and or blends will travel further underground from leaking pipes than methane currently does?
So the qualitative data from high deploy would indicate that for the specific scenarios, so to be very careful about this, that they did look at, that it travels up to maybe 20% further, but we don't know yet. We don't have a full understanding of how that was governed by the particular relationship between pressure, diameter, depth, and materials. So I think it's a bit too early to state that, and more to see if it's actually a problem, or if the safety factors that are currently there in terms of the setback distances are sufficient. Because how we really came about this, and I welcome the input from the operators in this as well, is we started with, okay, what's methane? What's the values for methane? And then how will they change? And then as we started to drill down into that and what the values are for methane, well, where did they come from? Where did you come up with those figures and values? So we went back to basics to try and understand the fundamental of behaviour first, to see what the setback distances actually are for, or hazard distance, I should say, actually are for methane. So we can see then how the setback distances relate to that. I'm not sure if that answers your question.
Well, Peter's question there, I think, yeah, I mean, I know when we are classifying leaks, or when we are, I'm not speaking now as a gas network operator, when we are responding to leaks on the distribution network, underground leaks, they will be classified according to their distance from a property, the pressure of the network, and the surface type. It may be simply a question that we change those classification charts so that we are responding quicker to leaks from hydrogen or hydrogen blended pipelines. So I think the first thing to do is understand the differences, and then we can, as an industry, work out what the correct response to that is. And that may differ. It may be a quicker response time. It may be a question of repairing things more promptly, and so on. A couple more questions here. There's one from Amir Sadrania. My apologies if I've pronounced that name incorrectly. It's asking questions about fatigue crack growth and the effect of assisted degradation for thickness calculations. I think that's probably a little outside the scope of this project, so I might pass on that one. Apologies to Amir there. If there's somebody better placed than me on the in the audience to answer that, maybe they can put an answer in the chat function there. From Andrea. And again, the name is partly missing. Andrea, Angela, I think it is, or Angelus. Thank you very much. Great presentation. I believe that in a blended methane and hydrogen pipeline, due to different densities, there will physically be transported as sections of methane followed by hydrogen. Do you see a concern based on different properties should there be a leak? So I think that's asking, will they stratify? Will you have a layer of the lighter hydrogen sitting on top of the methane?
We're not currently seeing any evidence of stratification, either, through this work or elsewhere. We're not seeing evidence of stratification either we don't foresee it within pipeline injection for the pressures and diameters that we're considering, and indeed the opposite, which is why we want to understand the point at which we believe perfect mixing will occur, or homogeneous mixing. In the event of a leak as well, we're not seeing evidence of that. And certainly there has been, there's limited experiments that I'm aware of on this, either small scale leaks in enclosed settings or so on, but there was data published by Sandia National Laboratories in the US back in September at a hydrogen safety conference, and they looked at unignited jets and measured concentration profiles in them for different blend ratios, and they weren't seeing stratification. They had some slightly unexplained behavior, between the methane and the hydrogen, but they weren't seeing stratification. So I don't believe that that's a concern. And just I should emphasize that I don't want to be giving the impression that hydrogen is radically different or terrible or awful. Rather, we're just trying to understand where the differences are and are they an issue? Because in many cases, the existing guidance may well be fit for purpose, but I think we need to demonstrate that.
My understanding is from some of the experimental work done that stratification has not been a problem. I suppose one of the things that we're interested in this project is at what point does it become a homogeneous, fully mixed material? Is it 1 meter downstream of the injection point, 10 meters, 100 meters, a kilometer? You know, I think it's generally understood it does become mixed. But and again, under what conditions, pressures, injection orientations, diameter ratios, all that sort of thing, does all of that take place? So the more we understand, the better we will be able to remove conservatism from you know, the engineering arrangements that need to take ultimately need to take place. I have a question here from, and I'm doing my best to pronounce this. If I get it wrong, please accept my apologies. But Dwayne Batterchaji, as you mentioned, at present literature for sand covers are only available. But what kind of other soil profiles will you be considering for the further research?
So we have tried to look at what parameters influence. So if we consider the materials and how we specify those or how we model them, is the parameters that we use in our software, or the porosity of those materials, which, as you can imagine, what we're seeing is bigger holes or areas that are not filled by the material. You'll have more rapid dispersion, and also the density, but more importantly, how that porosity is distributed. So what I mean by that is, you can imagine you could have, if you had sandstone, you could have small stones or small granules, or you can have very large ones. And the gaps between those and the channels through which the gas moves differ. So what we're trying to do is look at the impact of each of those parameters, what is most important, how that influences it from a fundamental behaviour, and demonstrate for values that are representative of sandstone, clay, materials that are typically used, what the kind of best case and worst case is. Because there's going to be no perfect cover. You're always going to have different layers. You're always going to have different distribution. You can have different moisture content. So what we're really trying to do is go back to the fundamentals and see what actually influences, what are the parameters of the material that are most important, so that should you come across our work and you know that you are most likely to have a given material, to look at where that fits within it. I don't know if I've answered your question very clearly there. We've taken values that are representative of sand, of clay, and so on, but we're also trying to look at this from a more fundamental perspective, so that if you had a different material, you could predict what might happen.
Okay, thank you. One final question that's in the chat box, and then we are a little over time, so we might call that a day. But there's one final one, but I think it's probably a little out of scope, but I'll read the question anyway, just for everyone's benefit. It's from Mark Gagan. Will later studies be done on the efficiency differences in hydrogen percentage mixes with methane, and the effects on burners, household appliances, and power generation plant with these different mixes? Will it increase their operational life or shorten it? So I think for the current scope of this research project, that's out of scope. I know we've done some work on that in the Network Innovation Centre in Browns Barn. One of our colleagues, we've done some work there with UCD on certainly on the domestic household appliances, but that's probably a study for a different day, I think. So with that being the last question, I would like to say thank you to IGEM for hosting this event, to IGEM and Pipeline Industries Guild both for co-promoting it, to Sheila for doing all the hard work and presenting all the fantastic information, to Brian, to Emmett, and to Neve, who are my industrial partners on this project, for all their guidance and support on the project. And I will just pass you back to John McCrory of Firmus and IGEM just to close this webinar. Thank you all for your time.
Thanks, Owen. Yeah, that was some fantastic research done by everyone involved. It's given us all an understanding of the sort of differences in behaviours between hydrogen and natural gas, and no doubt it'll be valuable information for safety cases and any technical guidance that's coming down the line for us all. Again, on behalf of IGEM and Pipeline Industry Skills, I'd like to thank Dr. Sheila and Owen and everyone involved. Very informative webinar. Again, IGEM will email out the link via IGEM TV once the IGEM is complete for anybody that wants to rewatch or use from their own companies. Thanks very much for tuning in, everybody. And again, thank you very much to Dr. Sheila and Owen, and hope everybody enjoys the rest of their day. Thank you.
Thank you.